Mm. All right, so if there are no questions, let's start. Um, so last time we we had a matrix, the rotation matrix over here, and we found that it has eigenvalues of the form 1 plus square root minus 1. And so we had to make sense of this square root minus 1, and we just called it I, imaginary number. So we extended our number system. Okay, to include I equal to square root minus 1. So that was the main idea. So we have this new number system. And we talked about how you can represent it geometrically. It's isomorphic to R2, so you can look at it as a vector. Okay. Are these notes on Quarkus? Yes, I upload them on Quarkus. How did we come up with the rotation matrix? Well, that's the, right, yeah, that's the transformation matrix. Exactly, yeah, exactly. Yeah, and then we just took, exactly, yeah, what Lindsay said. All right, so we had these complex eigenvalues coming from that real matrix, and 1 plus I, 1 minus square root minus 1, so 1 minus I. We computed its modulus. The modulus of a complex number is just the Euclidean distance from 0. So for 1 minus I, same thing. We take square root of the real part plus square of imaginary part. So again, we get the distance from the origin of 1 minus I, which is over here. This distance is square root 2. All right. Okay. Then we also computed the angle. You could compute the angle using arctan, namely theta is equal to arctan of imaginary over real part. So you get pi over 4. But in general, it's kind of tricky to compute arctan. So we often just use this equation here where we equate real part to the polar form to get theta, and then using the table. All right. So we talked about that. And finally, we're just gonna mention it, the Euler identity. So if you know that Z can be written in this polar form, then you can also further write it in exponential form. Okay. So just to explain this, EI theta is again defined as the following power series, I theta to the n factorial from n0 to infinity, right? So recall for real numbers, e to the x was defined exactly as this power series. So we extend this definition to complex. So that's usually how you do complex analysis. You start with the real definitions and you plug in I into the power series definitions, okay? How come we square -1 and not minus I? Oh, because you take the Euclidean distance, okay? So you, so again, if you want to find, let me do it below here. So if you want to find the modulus of A plus BI, you can look at it as a vector. So it falls somewhere over here, A plus BI. And what do? You look at the coefficients. So this is A and this is B, and you're looking for the distance from 0, 0 to AB. And this is just the A minus 0 plus B minus 0 squared. So we look at the coefficient of I. Okay, all right. All right, so let's, so we're not gonna do too much complex numbers because we only need them for matrices. So we're not gonna go very deep, but De Moivre is done in your textbook, so I should talk about it a little bit. So in your book, they have these exercises of multiplying complex numbers together. So the multiplication of two complex numbers can be done by distributivity. So 1 plus I, 1 minus I can be found by distributing. So 1 times 1, 1 times minus I times 1, and I times minus I. So you get 1 minus I, you get I times 1, and you get I times minus I. And if you do this calculus, you get 1, you get minus I, you get I, and then you get minus I squared, but I is the square root minus 1. So you get minus 1, right? These two cancel out, so you get 2. Okay, good. So that's how you do multiplication. Now, we just talked about this Euler identity. So if you manage to find the polar form for your number, so W is EI phi, and then you want to multiply your two numbers, Z and W, then you can just multiply their polar forms. Okay, so if you do that, what does it say? It says that the product of, so let me scroll to the right. So if you have Z with angle theta and some W with angle phi, then their multiplication will be the, somewhere over here, theta plus phi. So this will be ZW, and the angle will also extend. So depending on whether, ZW is less than 1, bigger than 1. So if they're both bigger than 1, you can imagine this will grow a lot. Okay, so multiplication is adding of angles. Okay, that's what multiplication in complex numbers does. Okay, so right, I was hoping somebody is going to ask this. So please be careful. This is not, even though we have an isomorphism, this is not dot product, right? Because dot product is the following. So you have one vector, you have another vector, and this guy over here is like the dot product. So let's make a distinction. So Z is A plus IB, W is C plus ID. If you multiply them out in complex numbers, you get AC, you get ID A, you get, what else? You get IBC, and you get minus BD, right? So namely, you get AC minus BD plus I AD plus BC. Now, there are some cross products here, and right, so you can see this AC minus BD, but yeah, this is definitely not the dot product of AB times CD, which is AC plus BD, right? So this is dot product, and this is complex multiplication. So that's a good question, and I'm happy you asked it because it's a common issue. Okay, Arya, is that okay? Good. All right, so that's what that's a way to see complex numbers. We just add their angles. That's the intuition there. Okay, and yeah, I have another one with high powers. So this is done in your book. If you have a complex number to some huge power, like n, then if you know its polar form, you can easily compute this as EIA and theta. And so you get Zn, and then you have cosine n theta plus I sine n theta. And to do this, we used Euler's identity. Okay, So De Moivre is just Euler's identity. That's all there is to it. Okay. What's the real purpose of complex multiplications, as those angles are not completely real? Well, this is a new number system. So when you have a new number system, a natural question is, okay, can you multiply your numbers? And the answer is yes. And you get that thing that we did. So new number system, new rules. Of course, you might ask why we even look at complex numbers. And the thing is, yeah, it contains the real. So many questions that you have on the real line, such as computing like sine x over x, can be extended to questions over the, the full complex plane. So, but yeah, I agree. There's many new things in this new number system that are not the same as in the reals. Is that okay, Lindsay? So, what was the question? Yeah, okay. Is that okay, Ismail? So it's just, well, I mean, it's a new number system. Yeah. Lindsay, so the complex multiplication is an operation that we define specifically for the field C. Oops. For the field C, is that the right way to think about it? Well, we didn't define it, it followed. You see, I didn't do any, I didn't have to define it. It sort of followed just from defining I to be square root minus 1. And from that, I built my calculus. But yeah, it's fun. You can think about it as like a new operation we define, because in a way, the new operation that we define is that I square is minus 1. That's sort of at the heart of complex numbers. Is that okay, Lindsay? So the question of answer over reals is only the case. Complex plane is only the case since R is a subset of C. Yes, yeah, exactly. So that's why we can answer questions about the reals. Can we write cis theta is sort of cosine theta, I sine theta? It's better, I don't know. It's better to, you can write, basically since theta is just EI theta. I will write EI theta. It has more information. All right, anyways, let's move on. Okay, what else? Okay, so yeah, and this is the De Moivre formula. All right. Now let's talk a little bit about Cn. So for that rotation matrix, we found the eigenvectors square root to minus 1i and minus square root 1. These were the two eigenvectors. And then, well, you might ask, okay, I understand that I is in complex numbers, but what about the vector I1? Where is that? In what space? Any guesses? Can somebody say on the chart? In what space I minus, right, yeah, exactly. Thank you. Thank you. No, not C cross R is, oh, I see, yeah, exactly. Perfect. Yeah, you can also see this as in, perfect. So it's in complex cross R, which is inside complex cross complex. So C squared. Perfect. So we define in general C to the n to just be the nth Cartesian product of complex numbers, okay? And we will talk about this later when we come back to isomorphism. We will talk that, in fact, C is isomorphic to R2. meaning you can express linear transformations over both of them, passing through this linear isomorphism. Like you have some map here, some map here, you can pass it to some map over here, right? Stuff like that. Like phi inverse, I guess. Let me say phi goes this way. All right, so yeah, so C to the n, each time you're gonna take 2 copies. So Cn will be R squared n, because each C is equal to the complex plane, okay? In C, some vectors that used to be linearly dependent are not anymore, right? No vector, so just to be clear, right? In R, everything is linearly dependent, right? Because everything falls on the span. So any vector is in the span of, I mean, it's kind of hard. You have to be in a subset of something. So everything is in the span of 0, 1, right? If this is like, or I guess first coordinate will be like this, 1, 0. So everything is linearly dependent in R, right, Ismail? Is that okay? Right, so these are our complex vectors. Now, another motivation for complex numbers is this amazing fact that the fundamental theorem of algebra. So let me go up here. So it says that if you give me any polynomial like x squared plus 1, and you want to find its roots, well, you cannot do it over the reals, right? This guy has no roots. This is always strictly positive when x is a real number. But if you allow x to be complex, so z squared plus 1, and you set this to 0, well, can someone guess what are the roots of z squared plus 1? Can someone tell me in the chat? What are the roots? Plus minus sign, perfect. Yeah. Rudras says, how will we go about finding the basis vectors for C, Cn? It's the same way that you did for Rn. So I will leave this. So for Rn, what did we do? We put 0 and then we put 1 everywhere else. So so let me do so for C, right? It will be C is the span of I, let me do it here. So let me do it step by step, because that's a good question. So for R2, this was the span of 1, 0 and 0, 1. So its isomorphic thing, the complex plane, will be the span of I, 0 and 0, 1. Okay. So from there, you can build the rest. So for Cn, you will have to look at its copy in R, if that helps. We can talk about this more after. I mean, we'll come back to all this stuff. Okay, so, right, so we have z squared plus 1, and the roots are z plus minus I. So what's the point? The point is that if you give me any polynomial over the complex numbers, it has exactly n roots. Of course, they can be repeated, you know, like z squared plus 1 squared. You know, like put another square there. So this guy has repeated roots. So yeah, but they will always be exactly n. And so that's another big motivation for complex numbers. So it will be the smallest such extension of the reals. Okay. If you're interested in the proof, it's a little bit involved, right? Because many of you have not taken complex analysis, but if you're interested, it goes by a thing called Liouville's theorem. So I will leave that to you. We can talk about it after. Okay. Any more questions about complex? Wasn't that a two-dimensional span though? Let's see. Oh, let me see. What am I talking about here? Let me come back to this. That's a good, let me be careful with this stuff. So let's see what we're trying to ask here. Yeah, that was definitely a C2. Sorry. This is definitely C2. Now for C, let's see, what are we talking about? So we want to generate any complex number. So like A plus IB. So let's see. Well, again, this is weird, right? So you can't really quite do this here because I know it's a little bit weird, but you should think of C as R, namely that C is really a number system. You know how you, let me write the line, right? You have integers are inside rationals, which are inside reals, which are inside complex numbers. So in a way, there is no like spanning of vectors. Everything is, it's a new number system that you like sort of enumerate your numbers. So it doesn't quite make sense to talk about span in C. But of course, you can talk about span in R2 and try to bring it back. So if that helps, right? But you can talk about basis by talking about R2, where you do know that you have span of 1, 0 and 0, 1. But we never talk about spanning vectors in the complex plane because it's a number system. Does that make sense to you guys? No, this does hold, but I'm saying as a, in your head, when you're thinking about complex numbers, you should think about them as a number system. Okay, so anyways, we'll come back to this stuff. It's very interesting. When we talk about CN, we will talk about span and all these things. All right, so any other questions here? So by C by default has imaginary and real, right? Yes. So C2 is span is not, no, C2, okay. The thing I wrote for C2 is fine. So you can definitely write C2 is the span of I0 and what else? 0, 1, right? Or let me write it in a different way. So you need to take Z like a complex number. So let's see. So you need to take one guy from here and another guy from here. That's how I should write it. So this is the same as when you talk about R2. This is really the span of one number and another number. Does that make sense? Yes, that's the analogy, that C is like the base for your extensions for C2. So this is the number system. Yeah, we will definitely come back to this. This is very interesting stuff, but CN is far ahead. For now, let's just talk about complex numbers. Yeah, okay. All right, so let's start with this new notion. So this is 5.1, okay? And we talked about complex numbers, and but we're gonna extend that. There's other interesting fields out there, other number systems, if you like, that people use. So we should talk about them. So the reals is a field. So it's a set with plus and multiplication. Complex numbers are also a field with plus and multiplication, right? So here we have x times y. Here we have z times w. It was this long thing, right? A, B, and so on. And so let's go through each of the axioms, and I will do them for real and complex, okay? So x plus y and y plus x. So for real numbers, this is obvious, right? So we have, x plus y when they're real numbers. This is by definition the way we build the reals. So this is now let's see for reals is clear. So let me call this for reals is clear. Let's do for complex. So you have z plus w, and how do you do it? You write it in terms of reals. So you have a plus ib plus c plus id. Okay, you group them together like this. Okay, and now you swap, because you can swap for the reals. So here we use commutativity of the reals. So then everything, you open it back up. So B, oops, what's going on? C, this is C. So, one second. So, yeah, and so then you have, you have C plus ID and A plus IB. That's sort of the idea, right? If you want to prove some axioms about your extension, you go back to your original object. Is that okay? Yeah, thank you. A plus C. Yeah, but we'll come back to these vectors later on. Okay. All right, so we also have associativity. It's the same thing. I don't think I have to do this again, right? So you will have let's see, z plus w plus I don't know, f, and then you have to like write everything, a plus ib plus c plus, let me call this something else. Big F. I'm running out of letters. And then E plus I little f. And then again, you group them together, as like this big thing. And then you apply the real, the associativity for the reals. Okay. So then you get back your Z plus W plus F. That's the idea. Okay. So I don't think that's complicated. So we define plus as normal addition, but that's not necessary, right? Yeah, here for the, right. I'm just going over the example. So plus, as you will see later on when we do a finite characteristic, yeah, plus can be something more general. So as long as it satisfies these axioms, yeah, plus is just an operation that you define. Yes, exactly. Yeah. F is a variable to C. So these three are, I'm just going over the example, but this field is more general. So these three things are complex. I'm just going over the example to help you understand this axiom. All right, yeah, I mean, you have another thing that we already talked about, that if you have 1 plus I and we had 1 minus I, right? You cross multiply to get your, you can apply cross multiplication. And we did that in the example. Okay, what else? The most interesting part is identity element. So for complex and reals, this is again the same thing. So 0 is again the additive element. So as in like the usual 0 and 1 as in the reals. So they are again the additive elements. So the identity again. Okay, so again, you can use 0 and 1 as the identity elements. We will do some examples where 0 and 1 can be very complicated things. But in the examples that we will do, for the most part, it will just be the usual 0 and 1. Okay. I know before I've seen addition and multiplication as being enclosed in a circle to symbols that aren't necessarily normal. That's right, yeah. Or you know what? You can also write it as plus F and multiplication F. That's another thing I've seen. So yes, I thought it was the set. I'm not sure what you mean. Ismail. Okay, so finally, we have inverse of addition and multiplication. So let me go to the next page where or let me see, I'll do it. Where is it? That's fine. Let me just have this axiom up here. So first, let's do it for the reals, right? So additive inverse is easy for the reals and complex. So, you know, if you have a real number X, then you just add is minus X, right? Is still in the reals, and X minus X is 0. For complex, you can do the same thing. So you put minus Z, and what do you have? You have A plus IB minus A plus IB. So you get A minus A plus I, B minus B, and they're both 0. Okay, so additive inverse is not hard. Multiplicative inverse is a little bit harder. So what does multiplicative inverse mean? Let's do the example. So you have X not 0 in R. So let me write this way. So X is in R, take away 0. Then as additive inverse, you can just take 1 over X, right? Because X is not 0. And indeed you have X inverse is equal to X times 1 over X, which is 1, right? Is that okay? Minus I is I cubed. Yes, that's right. Minus I is I cubed. We didn't have any triple products, did we? I don't remember. Okay. It was always 2 of them. All right. Now for complex, take Z to be C, take away 0. Okay. 0 plus I 0, if you like. So Z is equal to A plus IB, where A and B are not 0. Now, how do we define its inverse? Well, as someone asked on Piazza, why not just take Z inverse to be 1 over A plus IB? You can definitely do that, right? But this is not a complex number as you look at it. You have to play with it a little bit. So how do we do it? We do a thing called complex conjugation. So you divide and multiply by a plus ib, a minus b. Remember that we talked about that z bar is equal to a squared plus b squared, right? So you have a squared plus b squared, a minus ib. And so finally, you can write it as a complex number, as a true complex number. Like this. Okay, this is indeed a complex number. Is that okay? Is it clear what we mean here? So that's the multiplicative inverse. So let's see why. Let me go on the right. So over here, so you can still see it. So then we have z inverse is yeah, so you have a plus ib and times a minus ib over a squared plus b squared. So a squared plus b squared over a squared plus b squared, which is 1, which is the multiplicative inverse of the complex numbers. Okay, let me write it like that. Lindsay says, when I was doing the homework, whenever there were questions about dividing two complex numbers, I just multiply by the conjugate and evaluate. Is that the only way of doing it, or is it a shortcut for dividing complex numbers? Right, so either you do this, or you find the polar form and you multiply them, right? So Lindsay asks a nice question. So suppose you have z equal to r ei theta and w equal to rho ei phi, and you want to divide them, then this is just r over rho and ei theta minus phi. So that's another way. Is that okay? Okay, good. All right. Okay, so yeah, so this is the additive inverse. I typed it as well. So that's how we define it. So indeed, complex numbers are a field. Right, I do the multiplication here. Some other examples that we're not gonna go into, but I just wanted to mention. So these first two, we're not gonna go into them. So these two are also fields. If you're in engineering, in physics, quaternions show up a lot. So this is a further extension of complex numbers defined by these operations. So so I, j, k are not specific. So in our case, we knew that I is -1, but this I, j, k are just now symbols, and they satisfy those relations. Okay. Anyhow, so this is an extension of complex numbers, and yeah. Okay. So this will also be a field. Also, the set of ratios of complex polynomials is also a field, meaning you can add complex polynomials because you get another complex polynomial, you know, like Q1, Q2, P1, Q1, P2, Q1. It also has multiplicative inverse, right? So PQ times PQ inverse is equal to 1, right? That kind of stuff. For quaternions, do you use coordinates to evaluate them? Oh, I see. Yes, yes, yes. Yeah, this is yeah, we're using the higher dimensional. That's right. This is like the higher dimensional for complex numbers. Yes. Yeah. Yes, yes. Okay, but yeah, we're not going to go into this. I just wanted to give you that there's um, other kinds of fields that people are interested. We're going to go into um, finite fields right now because it's also covered in your book. So I'm going to talk about that right now. So yeah, once you have a field, then you can do linear algebra. So you can define matrices of complex numbers, matrices of quaternions, matrices of complex polynomials. Okay, so you can do linear algebra over those fields. Okay, so that's the power of it, of knowing that something is a field. You can then start doing a linear algebra. Okay, everything's so good. All right. Now, in your book, they go over an example that we're also gonna mention in this course a lot. These are called finite fields. So let's go slow on this. So yeah, first let's talk about modulo numbers. So here we talk about modulo numbers. Let me repeat it. So if you give me an integer m like 100 and you give me some prime number like, I don't know, 2, then maybe something more complicated, like 3. Then you can write 100. You take the highest multiple, right? So there is some number q, and then wait. So I want to put like 99. So what do I want to say? Yeah. So you have 99 plus 1, right? So this is I don't remember. So this is 3 times some number p, if you like. What do I call it? I call it q. Okay. So q times 3, and this is the remainder. 33. Yes, thank you. Let me just write it like this. I don't know. My brain doesn't work that well in the morning. So and this is the remainder. So and this is p and this is q. So modulo of 100 modulo 3 is equal to 1. Okay. So you find the highest multiple, and then whatever you're left with is the modulo number. Okay. Hopefully that makes sense. So that's how we define modulo numbers. Oh, I did have an example. Okay. And then, yeah, when m is 5, same thing. So this is equal to 3 times 1 plus 2. So modulo of 5, 3 is equal to 2. That's okay, right? I don't think that's confusing to anybody. All right, so that's modulo numbers for you. And right, but the remainder can only go up to whatever the prime number is. So you only have the following possibilities. So, we found that 103 was 1, but so is, I guess, 4, right? So 4 modulo 3 is also 1, right? Because you have 4 is equal to 3 plus 1. So that means that how should I say it? Yeah, I can say it like that. So 4 plus 100 belong to the modulo class, if you want to do it that way, of 1, 3. Now, this is a little bit playing with definitions here, but all we're trying to say is all that meaning that 4 modulo 3 is 1 and 100 modulo 3 is also 1. So what they say is that think of this as an equivalence class, i.e. a set of all x integers such that the modulo of x given 3 is 1. Okay, is that okay with you? So that's what they're trying to say, that this is an equivalence class. So you sort of group together all the integers that have the same remainder. Okay, so if this, we'll come back to this, but that's the big idea here. Okay, all right, we'll come back to it for sure. So okay, you have those P equivalence classes, and our definition for finite P is this one over here. So let me finish here. So we take it to be the remainders, so 0 to P minus 1. And now, like someone talked about, addition and multiplication are not quite the same as before, right? So here we define plus of this finite field P to be the following. You give me 100, let's say like this, and you give me 4, and we define their addition to be the addition of the integers inside it. So 100 plus 4. Okay. And yeah. And similarly, the multiplication of 100 and 4, this is 3, will be the product of their integers, like this. Okay. Right. So, okay. So let's see. Yeah, we will. Right. And then this is in your exercises, so I'm not really allowed to talk about it much, but in your exercises, they ask you to show that this guy is a field, and I only did 2 of them for you, so you can use my idea to do some of the exercises. So I will leave that to you because apparently it's homework, so I'm not allowed to touch too much, but okay, so we can talk about it more on Tuesday in the textbook for FP, and posted some of the suggested problems. Yes, yeah. All right, thank you, everybody. So we'll continue on Tuesday from where we left off on FP. Yeah, thank you all. I'll stick around for questions. Yeah. So, Lindsay, you can talk. Yes.
Hi, could you go back maybe to
you're
slide...
a guy. I'm sorry.
Yeah, sorry.
I'm sorry. I'm really sorry.
That's okay. Common happens all the time.
Okay, I'm sorry.
I think slide 22 or something. Okay, maybe a bit after. It was when you were talking about showing the examples in matrices of these different fields.
Oh, okay, yeah. Let me find it. Oh no, you're right. It's in after. Where is? Right. Yeah.
Yeah, here. Okay. So, because I've had difficulty understanding complex numbers for a while, just like kind of intuitively understanding what they are. And so like looking at this, like with the first one, it looks like this is kind of a two-dimensional coordinate system, right? But then it's almost like with the imaginary part of the number, is it almost like thinking that there's a third kind of hidden dimension in which the complex part lives?
Why do you say hidden?
Well, because we only have like two dimensions in this space, right? But then there's this other part of the number, like namely the
Oh,
imaginary
yeah,
part.
you're right. You're right.
Yeah.
Right. So, yeah, this is very tricky, right? So, you like they sort of ask you to do two things at once. First, you have to think of complex numbers as a number system. So there is no, the dimension is one in the complex numbers. Um, like, because they're numbers, like the rationals don't have any dimension. But then the complex numbers are isomorphic to R2, in which case I has this hidden dimension that you can go up and down. Let me see if I understand what you're. Yeah, so there's two complicated. First, this C as the number system, and this is not a vector. There's no vector here. So that's why, for example, dot product of ZW makes no sense, because ZW don't have components, right, Lindsay?
Yep.
Because dot product means V times V times, I don't know, U is equal to the summation of VI UI, but there is no such thing because these are not vectors. But on the other hand, if you go to its isomorphic copy, then yeah, you basically multiply real part and imaginary part, but we never really do this. But yeah, I'm not sure. Like, yeah, you can think of C as isomorphic to R2, or you can think of C as a number system. And when we do linear algebra, we do the first. We think of it as a number system. We don't think of it as a vector. So this is where, here is where we do linear algebra. Because
So I think
because I agree. If you do, I think now I understand what you're saying. If you do linear algebra here, you have tensors, because it will be like a two-dimensional thing, right? Because you will have like the inputs, like 1 plus I is a number system. But then if you look at it as a vector, then you will have 1, 1, right? Right, Lindsay?
Right. Yeah. Right.
Yeah. But we do linear algebra here, because we want to do like this linear operations, whereas here you have to do like Einstein notation. This is a tensor. This is a matrix.
Right. So I think what's motivating this does make sense, but I think originally what was motivating the question is because I remember first being exposed to imaginary numbers in high school, talking about certain polynomials or well, I think it was just parabolas that like didn't intersect the x-axis, and then like you're using an imaginary root to find a real solution. And so I think it was this kind of idea of how can we use a quote unquote imaginary number to find a solution that exists only in the reals. So
Only in the reals? I have to see this example. Okay, I will look for it. That will be interesting to see. Because I see, yeah, that's interesting. I want to find it.
Well, what I'm thinking is because like, you know, you
So you
have,
had some polynomial, right? That's what you're saying, and you
well,
wanted to find.
it's nothing fancy. It's just like, you know, x squared plus one,
Right,
the roots are going to be plus minus I, right?
right,
But every point along the parabola is a real number. That's all I mean, right? And so
right.
and so it's just the question of like, how do we get a root that like isn't that doesn't exist on these axes? But I think it makes sense now. So
Okay,
yeah,
but
thanks.
you said you came back though.
I'm sorry.
You said you found the complex roots, but then you came back.
I just meant because, you know, you're plugging I into the equation, and
Right.
then obviously you're getting what, zero, right? Or like, you know,
But
any
did you do like some actual question where you had to compute something and come back to a real answer? Or
uh
okay, I will look into it because I'm
yeah,
interested. I'm sorry. I will. Yeah.
okay,
Anything? Okay. Is that okay?
yeah, thank you.
All right. Who else? Oh, Kelly. Please. Tell me. Are you there? What's the problem?
Yeah, no, sorry. I meant like I'm confused about. I was trying to understand his question as well, and now I'm confused too.
Oh, which question?
Lindsay's question.
No, but which? Because he asked a bunch. So which one?
No, I mean like the one where since you have plus or minus I as a root, and when you put it back on, it's not
Oh,
like part of it.
when you. Yeah, like I mean, I think no. All he's trying to tell you that x squared plus one, right? If you allow x to be real, this is never zero, right? Right?
Oh, okay.
Like it's never zero when x is a
Because
real
X has
number.
okay.
Yeah, but then if you extend your number system, um, if you extend your number system to the complex, then yeah, x, let me write z since I always write z, then z squared plus one can be zero, when z is like plus minus I, right?
Yeah. And then you wouldn't be able to draw that in like a
Oh yeah, you
proper.
can, sure.
Hmm?
Yeah, you mean the z squared plus one?
Yeah.
Yeah, you cannot. So that's a very good question. So z squared plus one is a guy that goes from complex to complex. And this is R2, and this is R2. So if you were trying to do the same thing, you would get a four-dimensional 4D picture, right? Because this
Oh,
is the domain, and this is the image, right? X squared plus one
yeah.
goes from R to R. So you can draw it in the plane. But this guy goes from R2 to R2. So it would be like in 4 dimensions, which I cannot
Yeah.
access. Yeah.
I get it now. Thank you very much.
What are the suggested problems and where can I find the slides? Slides are under my module. And the suggested problems, you look around a little bit. I mean, I don't remember exactly where does he put them? He had these suggested problems. Yeah, Rudrash, you can ask your question. You can open your mic, make it easy for us.
Yeah, I had a question about the finite fields example you gave with the
Yeah.
modulo
Yep.
thing.
Yep.
In the definition, it said that the finite field f of
Sorry, one second. So Ismail, go to assignments and then look into the reading quizzes. Okay. All right. Let's come back. So yeah, go ahead.
in the definition of finite fields, it says that the elements of f of p are like from 0 p all the way to p minus 1 p. So then how are we able to include numbers like 4 and 100 if P is 3 in this example.
Right. So how shall I say this? So mm, so this is a very confusing notation. So these are equivalence classes. So exactly like you said, so 100 3 is equal to 1 3.
Oh, I
That's
see.
why.
So like each element in the definition refers to like one equivalence class.
Yeah.
Oh, I see.
So
Okay.
and then this is and 4 3 is also equal to this. So then you can do calculus with 104 because they're both the same element.
Yeah.
Yeah.
Oh, I see. Okay.
Yeah. No, that's a very good question. Please ask this during class. That's a good question. Okay.
Okay. Okay. Thank you.
Okay, I don't see anything else. Any other question? All right. Okay. So see you guys on either today at night at 7 or on Tuesday. All right. Thank you. Thank you. Okay.